Great. Good afternoon, everyone. I would like to start with the title of the presentation, which is Simulation-Based Framework to Evaluate Resistivity of Cooling Strategies in Building Under Climate Change Conditions. And I'm very delighted to be invited by IBIPSA England. To be honest, my #1 community is IBIPSA World, and I'm benefiting from all these small IBIPSA families all over the world. Because it gives very clear ways on how to tackle the challenges related to the built environment and with buildings. And in this sense, I'm associated, I'm a member IBIPSA Netherlands and Flanders. We don't have an IBIPSA in the French-speaking Belgium, but I'm associated with the Dutch-speaking IBIPSA, and for sure I'm also a member of IBIPSA World. Now I need to acknowledge very fast the IEA Annex 80 members, all of them, and my team members of the project occupant that we have here in Belgium, because behind this simulation framework that I'm going to talk about, that is mainly related to building performance simulation, all those people are contributing, and I cannot name them. So I just need to make sure that I'm not talking here in my name. I'm talking in the name of a big group of people. We're working since 2 years around this topic. So as you know, the latest publication of IPCC that was published last year, end of 2021, there is a new IPCC report, and there is new scenarios that are worse than the scenarios from the report of 2016. And as you see in this graph, the most recurring events in the near future will be mainly extreme heat and mean air temperature increase, and even fires. And fires is the threat #1 in Europe, and especially if we are in the northwest of Europe, all of us, we have a lot of greenery around us, we have a lot of forest. The challenge that we see in south of Europe related to Portugal and Spain, we have to foresee it. And therefore, air quality and association with a temperature increase will be the threat #1. Climate change will not wait for us until we take the correct measures. In this context, in our Annex 80, we wanted to define resilience, and we needed to be more specific. We wanted to define the resilience of cooling characteristics and the risk factor around the overheating risks in buildings. And after a long work of investigation, we collaborated with the United Nations, we collaborated with the United States Green Building Council RELI rating system on resilience and the definition of resilience. We had to distinguish 4 stages related to the term resilience, mainly the vulnerability phase, the resistant phase for a building, the robustness, and finally recovery. And as you can see, robustness entails failure. So the key message I want to talk about with you today is that when we talk resilience, we must have a shock, we must have a disruption, and we must have a failure. Without failure and bouncing back after a failure, we cannot name the building resilient. And that's what we are trying to investigate in the IEA Annex. We are even investigating the events and the shocks that can cause a building to fail. And since we are concerned with comfort, like what we saw with the heat dome in Northwest, in the North American, in the context of North America, in the West with Vancouver and what happened last summer, that's kind of events that we are talking about. So in this context, in the annex, we started to try to define some thermal condition, design thermal condition, and juxtapose them against minimum thermal condition and critical thermal condition and failure conditions with different future weather files, short waves, heat waves, 200 end of the century, mid of the century scenarios, to make sure that we can test our solutions and our sizing of our cooling technologies, whether they are passive or active. And in this sense, we are looking at resilient cooling characteristics related to the overheating exposure risk, the exposure severity, the ability to adjust to this exposure, and for sure the ability to recover or bounce back after we were hit, for example, with a long heat wave or an extreme heat wave. And for sure, in our approach, we are coupling heat waves with power outage, because it will not be surprised that when there will be a heat wave, most probably we'll have power outages. The third parameter we did not address, which is fires. But it seems that the extreme events around the world occurring in the recent years are confirming that heat waves will be coupled with power outages and fires. So it's very important to learn what happened in Australia 2 years ago. So in this context, we are looking at these factors, and we are trying to define some frameworks that can allow us to run simulations that take into account these multiple criteria, whether we are taking time on the short term, a very short heat wave, or 100-year long scenario. The scale can start with a single zone where you are grouping all occupants in one safe or refuge space in the building where you are providing cooling, or if you are talking about the whole system, HVAC system, the building as a whole, the neighborhood, the district, up to the city scale. And for sure, we are taking into account the vulnerability to different shocks like heat wave, power outage, air pollution, by fire, and so on. So this is overall the frame that we are operating in. And what I would like to share with you, maybe I'm sorry, the presentation is very bit fast, but I want to share the maximum, and this is a recorded event, so you can later come back to the slides. So far, we managed to publish in the IEA Annex 80 a framework to evaluate the resilience of different cooling technologies. And this framework is based on simple use of future weather files and the exclusion or inclusion of urban heat island effect. And based on that, we try to find or develop a framework that can cater for the whole world. So when we mapped our work, we looked at all the planet so that the framework can be used worldwide in different cities. And as you can see here, we have different representation of cities. Then becomes in this framework, you need to define the building characteristic that will be used, whether you are using a shoebox approach representing the building in a multi-zone, or simply the best test series 610, 600, 620, or if you have a real case studies that you have really monitored data and you want to represent in the model. So as you can see, we referred mainly to Ashty 169 because it's the most accurate. It's based on cooling and heating degree days, representing a very accurate climatic characteristic of the world. And from there, the framework goes with the next step with defining the archetype, or simply the architecture archetype or the representation of the building, whether it's an ideal building model like the best test, or it's a theoretical model made by experts. Like we see a lot of benchmarks published. There is an European database, there is a American database, and for sure the last option can be a real case study where you are using for running the simulation and testing your cooling technology and comparing them to check how severe will be a heat wave or future climate change. After moving from the archetypes, we used Ashty 189.1 2017 because we had a difficulty to use the passive house standards. It was not appealing to use it all over the world. We found Ashty 189.1 more appealing because it defines high performance building all over the world using the Ashty climatic zones. So you can have it from Alaska till Madagascar, and this allows to have a more accurate representation regarding the characteristics from the envelope regarding air tightness, heat transmittance, and so on. And this is back again, like a summary of the first part of the framework. The second part of framework, we are talking here about the comfort model that will be used, and the cooling technology that you want to check in order to assure comfort and make sure that people can survive during extreme events. So far, we in the annex working on fully air-conditioned buildings and free-running buildings. Unfortunately, we were unable to have a common international consensus on how to evaluate mixed mode or hybrid running buildings, because this is still an issue that is not having international agreement. And we are fluctuating between ISO standards, EN standards. We are even working sometimes with TM59 in the UK, very interesting standard. And all the work of CIPSI is very, very good. But we are between ASHRAE, SEN standards, and for sure ISO 17772 in the two parts are our reference. So far, just to give you a glimpse, we are using a very interesting indicator which is called the Severity indicator, or the Ambient Warmness Degree indicator, which evaluates the severity of the outdoor warmness by averaging the cooling degree hours calculated for the base temperature. For sure, the base temperature can be varied, and based on that, we can estimate the ambient warmness degree. And another important indicator we are using also, it's called the Indoor Overheating Degree, which is developed of one of our members of the annex, Hamdi, and in this index we can introduce different thermal comfort limits for different zones, so it can allow for a multi-zonal approach, and then you can distinguish the sleeping room, for example, compared to the living area, and you can put more stringent requirements or thresholds regarding your comfort requirement in regard to the occupancy and the expectation of comfort. So we move after that to this classification of the cooling technologies that we are trying to test in the annex. And as you can see in the annex, we are working mainly on 4 families of cooling technologies. Technologies that are reducing externally the heat gains, technology that remove sensible heat from indoor environment, and category C, personal comfort technology or systems that can be in the same zone integrated, and finally technology that can remove humidity or latent heat in the indoor environment. Well, I'm coming to an end. I want to respect the 10 minutes limit, but if you ask me in a short word, what is beyond the COP26, the next COP26 is will be in my origin country, Egypt, in Sharm el-Sheikh. Well, it is to prepare for climate change while living under the condition of climate change, because climate change, like I told in the beginning, it will not wait for us. So we need today to live with overheating problems and events, talk about how we will have environmental friendly refrigerants, how can we tackle heat waves, can we run mixed mode operation of buildings, but with a standardized approach that will not jeopardize the comfort condition of people and not also abundantly use energy and resources to just space condition the building. And for sure, low impact cooling will be a necessity to fight climate change and assure the resilience in the coming years. I share with you those 2 publications just as samples, but I invite you to look at our website of the IEA Annex. And for that, I thank you, and I hope you can share or interact through questions. Thank you very much.
Thank you so much, Shady. Really fascinating and ambitious work. And again,